Good afternoon, everyone. Welcome. Thank you very much for joining us today. My name is John Hyde. I'm the Assistant Director of Career Development and Alumni Services for the Data Science Institute here at Columbia University. Thank you for joining us. Today's seminar is an iCubed, which stands for Institute, Industry, and Innovation. These seminars connect our industry affiliates to our students in the larger Columbia community to explore topics at the forefront of the industries. We invite data scientists, engineers, researchers, and others from our affiliates to give talks on recent projects or case studies they've been working on. During these educational events, we encourage attendees to ask questions via the chat and Q&A feature, and we'll leave that available, leave some time for you to open that up at the end of this session. Today, we have a data scientist from Capital One speaking, and today's talk will be counterfactual explanations via latent space projection and interpolation presented by Brian Barr, a machine learning researcher at Capital One, and Matthew Harrington, who's a PhD student at the School of International and Public Affairs here at Columbia. Welcome, gentlemen. Brian and Andrew, thank you so much for joining us today, or Matthew, joining us and being with us today. We'll kick it off and hand it over to you.
Awesome. Thanks for the intro.
Pleasure.
Let's pull up the slides. So, John's introduced the title of our talk.
I got it right, didn't I?
You did. You nailed it.
Okay, great. Thank you.
So I won't belabor the point. I do want to highlight this is very much a collaborative effort with Matt. He spent some time with us over the summer as an intern, and I think without his contributions, this work wouldn't have gotten to the point that we're at right now. So big thanks to him. Basic outline for the talk, pretty boilerplate agenda. We're going to talk about the motivation for the work, what the method is like, some experiments that we ran to verify that the method that we've dreamt up actually works. Getting into results, we'll discuss a little bit about some unique visualization that Matt discovered along the way and conclusions at that point. So I'm going to try to set the table with motivation, right? None of this should really be all that surprising. We are in the midst of a sea change in using machine learning for a whole host of things where every day you find another application that is state of the art, whether it's computer vision, NLP, what have you. Along with that came a series of DARPA funding projects on explainable AI, right? And that provided a way to provide feature importances essentially for these black box models that are increasingly more powerful. Our point of view is that not all of these explanation methods are applicable to all the personas. And when I say personas, I mean everyone from model developers to, say, business analysts that are responsible for those models, model validators that ensure that they're making appropriate use of data and appropriate predictions, and even people downstream of, say, binary classifiers that are potentially impacted by the decisions that would be based on these predictions. In particular, there have been cognitive studies that show that counterfactual explanations really help inform the people impacted by decisions to understand what could have been changed to alter the outcome of a prediction, right? And most of the work in the literature is targeted at those end customers impacted by the decisions. I think there's a strong use case ahead of that. Before the model is even released to be in production and used, we should empower all of those business analysts and validators to ensure that the model is working properly. And I think counterfactual explanations help do that for that body of users. Now, just to firm up what I've been mentioning, here's the definition of counterfactual explanation. It represents the minimal change to a data sample in the input that would change its predicted classification. And typically when we think about counterfactuals, it's from some declined or disadvantageous, unfavorable classification to a more favorable outcome. I also want to highlight counterfactuals are often used in the framework of causality. We're not leveraging counterfactual in that same notion unless you picture the model as your world. These are all changes in inputs that would change the classifier's prediction. This has nothing to do with real world causality, just to clarify.
And so basically we're the three big questions that we're looking at here is this one kind of sums up what Brian just said. How can we change our classification score to a desirable result? And in this case, we're looking specifically at binary classification. We show that the method kind of works for to some degree on things with multiple classes, but we specifically focus on binary classes. The second one is that there's this really interesting question of okay, let's have a machine learning model, in this case, an autoencoder. What does it produce when it sees a class that it's never seen before? It's trained on a certain class of data, and then when it's given another class, what does it come up with? And the third thing is, what does this tell us about the classifier's decision boundary? What does that look like in a sort of, how can we interpret that as humans?
So this is an eye chart. Let's just take some time and walk through this flow chart of how all of the data and models that we put together in the algorithm. For this, we're going to motivate this using MNIST digits, since it's visually intuitive. Let's put it that way. And tabular data sets are less intuitive, even though that's our focus. But let's walk through this. So say we had the binary classification problem where we wanted to be able to classify 4s from 9s. And we will take arbitrarily that a 4 is a base disadvantage class and 9s are the target class, the preferred classification. Counterfactual essentially is a search from your starting point, from this 4 to some direction, in some direction to the decision boundary. That's where the definition of minimal shift kind of helps guide that search. We've taken a different approach in guiding the search. Essentially, we come up with a projection of our base class to the target class. This green model in the middle here is an autoencoder trained purely on the target class. So if you input a base class sample, it will change it in a suitable way so that it matches the target class distribution, but comes out the other side looking like a 9 very clearly. What this helps us do is provide a start and an endpoint for that search, quite frankly. We move from our start and endpoint into a second autoencoder using just the encoder portion of the model, where we'll take both the input and the projection and embed it in a common latent space. If you're not familiar with an autoencoder, let me back up just for a second, just to give the 30-second TLDR explanation. It's a deep learning generative model that essentially is tasked with taking an input, performing some level of compression down to a latent representation of reduced dimensionality, and then re-encoding it back out to recover the input that you put in. Sounds very simple, but it's very useful in a lot of contexts. We're using the unified encoder to put both our input and our projection into a common representation. And we can do linear interpolation between our start and end point in latent space and just walk along that line until we find something that decodes to be the counterfactual just across the decision boundary from the original starting point. And I think you can see how essentially the classifier wants for you to become more like a 9, it wants the top of this 4 to be closed off. And in this particular instance, where it's just across the decision boundary, it's not as closed off as the projection sample, as an intuitive example of how this whole thing hangs together. I think at this point, it might be a good point to stop and see if there's any questions at this point. We'll get into details about each of these bits in a little bit.
Nothing popping up in the chat, if that helps, but people could come off mute if you're okay with that.
Yep.
To ask any questions people have. Feel welcome, folks, if you're there.
Yeah, can I ask a question? So good afternoon. This is Nikita Seleznev from Capital One. I'm a colleague. Hi, Brian. That's a very interesting topic. I was just wondering, I mean, why do we need the latent space? In principle, we could just not reduce the dimension and have the same mix of the two features. I mean, just if I am correct, maybe I'm not.
So one of the challenges with just doing it in input space is you won't necessarily remain in sample and faithful to the underlying distribution of the input space. Let's put it that way. And we've seen one of the counterfactual methods that we look at is gradient descent in input space. And it'll typically make a bunch of smaller changes that are more diffuse, and you're out of sample at that point. The goal of using a latent representation is to remain in sample so that it should be an actionable, realizable counterfactual that you end up with.
Okay, thank you.
Good question. Yeah, you can imagine a whole host of ways to generate counterfactuals and search directions that you could go in. And there's a large body of evidence on how others have done it. This, I think, is the most, in some sense, the line search is very simple. And then the other sense is, I think, a little bit more philosophical. And Matt always kind of cringes when I bring this up, because it's not directly data science. If you think of this, you could think of credit card applications. You can think of this as digit classification, right? There are inherent properties that are advantageous and disadvantageous between being a 4 and a 9. What this projection gets you is it holds most of the and maybe this is even a good spot to step forward. It holds most of the good qualities that you already have and focuses its changes on really the fundamentals that are required to change your classification. And so here's a host of examples where we have the input samples and their projection. And you could see a lot of these, like especially odd 4s. This 9 looks just about as odd as that 4. I think it's really striking examining these MNIST examples to kind of back up the target autoencoder projection process really only changes the air quotes around bad qualities and retains your goodness, which I think is a really kind of deep philosophical statement about this process.
And my sort of take on this too, for this slide, to point out some specific things that might make it a little more concrete what Brian is saying. You can see that certain aspects of the fours. So these are the projections of the fours using the target autoencoder. You can see that some of the fours have certain angles, and the angles are reproduced in the projections. You can also see like the line thickness, certain widths of the circles sort of correspond to the width of the gaps between the fours. And so you can kind of see that like there are certain aspects that the autoencoder is picking up. And that's really exciting because as research into autoencoders improves, we're going to be much better at like controlling specifically what aspects get transferred. So yeah, that's just what I wanted to say about that.
Matt, do you want to handle this next bit, especially since it's the formulation of the autoencoders that we use?
Yeah, sure. So specifically, we started off this experiment trying to use autoencoders, and the standard autoencoder is just a neural network in, neural network out. And we found that changing to the variational autoencoder, which does like it has a very similar purpose, but instead now we have two aspects in the optimization problem. One is that we want reconstruction error to be small. You can see that at the bottom in terms of mean squared error. And then the other aspect is that we have this prior. So we want the latent codes to be close to the prior, which we measure through KL divergence, which is that term on the y-axis. And without getting into too much of the technicality, there are these competing forces between how close your latent codes are to the normal distribution and how good your reconstruction is at the end. So essentially, what we're doing here, there is this innovation, the beta variational autoencoder that basically put a weight on these two terms. And varying that beta and the size of the latent dimension gives us all of these points here. And you can see that there's sort of like a furthest to the left and furthest down along that frontier. This is what's known as a Pareto frontier. These are the points that we consider to be the ones that we want to select because they both have the lowest MSE and the KL divergence for like it's not to the right of that curve. And so those will be the best points for any, and which specific ones we picked will be based on the other metrics that we're going to be looking at. But then the main point here is just that there are these competing forces of reconstruction and conformity that we actually use to our advantage. And so this is the algorithm for the diagram that we showed above. So if there's any questions as I go through this, please feel free to ask them because I don't want people getting too lost in the technical details. So essentially, this is the algorithm. We first off start with a parameter p. So this is the probability that basically the probability is set by the experimenter based on where they want to split the two classes. And so Bobby in the chat asked, is the best counterfactual a 50-50 prediction? That is kind of chosen by where that line needs to be in terms of the probability coming out of the classifier. Sometimes it's better to have higher, lower, especially if there's class imbalances, but I won't get into that once. Anyways, and then a tolerance we define here away from that probability. So we just want to be in that gap on the other side of the target, but then within a tolerance. And just some notation, we have a classifier F. We have the VAE that's trained on XT, and a VAE that's trained on XB and XT. So the target, okay, we're denoting by a subscript T. Unified, we're scripting subscript B and T for base and target. And then we are taking S samples alpha. We're just taking a number of points along the line 0 to 1. Okay, and then, right, so the first step is we take our base, our XB, and we pass it through the target autoencoder. So phi of t here is just the, it spits out another X. But this is now a target because we've only trained it on the targets. So we've called that X hat t. And now we take both XB, the base sample, and its target projection, and we're passing it through to get through the unified decoder. That's a unified encoder, which we've denoted var phi, to get the latent endpoints, the code of the base and the code of the target projection. And now for each little spot along the line, right, alpha is just between 1 and 0, we're going to do linear interpolation. And so we go between the two endpoints, alpha SCT plus 1 minus alpha SCB, which is, alpha distance between the two. And this is our candidate counterfactual here. We're not accepting it yet because we don't know how good it is. So we first have to decode it, which is psi there. And now we check how good it is. And so we pass it through the classifier F. If it's if it's less, it's like within that tolerance from the probability, and it's in the right class, so it's classified as a target, then that is our new counterfactual, and that's the one we return. And so from a higher level perspective, we're taking a lot of points along this line. We found these two endpoints. The other endpoint came from the target autoencoder, and we've put them in this unified input space. We take all these points along it, and we check each point, see if any of them meet our criteria. If so, we just accept that counterfactual point. So are there any questions at this point?
Not seeing any in the chat.
Okay, since the method is crystal clear, let's step forward to the experiments that we ran using this method. What we're going to show today is based on 3 public data sets. You've seen a little bit of MNIST already. We're going to take a look at the UCI credit default data set and the Lending Club data set as well. We're going to compare our method, which we call SharpShooter, against gradient descent in input space, and as well as just gradient descent in latent space to see how it all shakes out.
And then, oh yeah, sure, you want to go?
Well, I was going to say another aspect of the counterfactual search is measurements of goodness, which I think Matt's going to cover next.
Yeah. So basically, counterfactuals are kind of interesting because it's hard to say what is a good counterfactual, which is not surprising because, like, what 9 is the closest to a given 4, or what person who didn't default is closest to somebody who did default. These are very difficult questions to answer. So these are some commonly used metrics that sort of help answer that question. So the first one is just the time, which is something that SharpShooter does seem to do particularly well in. And this is the time used to calculate one counterfactual. The next one is validity. So this is also very important. So these two are kind of like incontrovertible. That validity is when you generate a counterfactual, you want it to be classified correctly. If it's not classified correctly, you've kind of failed to produce a counterfactual because it's not in the right class. And so the other one, proximity. proximity here, we've changed. This is basically like the closeness aspect that Brian had been talking about. We want it to be close to the original sample. In this case, we take it as the Euclidean distance between its encoding in the unified space, the counterfactuals encoding in the unified space, and the base spaces encoding the unified representation space, which is a little, usually you do it in terms of input space. We didn't find that the results were that different, but we thought that because we were really interested in producing things that were close in terms of the manifold, we thought this might be a more convincing measurement.
Also handy to avoid doing distances in mixed data sets with continuous and categorical variables. That distance calculation is not necessarily concrete. Like a Gower distance would rely on you applying some weighting between the continuous and categorical. In the representation space, it's all continuous variables, so we can very conveniently use Euclidean distance.
Yeah, definitely. And the last one, or the second, there's a couple more. Sparsity. We want the literature is concerned with sparse transformations, because there's an assumption here that like if there are fewer attributes that are, it's easier to explain to somebody a sparser explanation, counterfactual explanation, as opposed to one that's not. So here we just measure the ones that were that changed, measure the dimensions that change.
Yeah, what's that rule of thumb? Humans can hold in their mind 5 things plus or minus 2. So I think that's the rough guideline in what would be like an optimal from a human being able to hold it in their head kind of view.
And then this one and the next one are things that we've sort of promoted, but that have been motivated in the literature to some degree. In this case, we check the counterfactuals, how it does under the unified autoencoder. So basically, we're passing the counterfactual through the unified autoencoder a second time, or the first time, which produces a reconstruction of it. If that reconstruction is very far from the original counterfactual, we think that original counterfactual isn't probably close to the data distribution. So this is sort of something that we track. And then in a similar way, we might not be concerned with the fitness from this perspective of the unified autoencoder, but instead maybe we're more interested in how passing it through the unified autoencoder changes its classification score. Because if it changes again a lot in terms of classification, then it probably something funky happened when it got passed through the autoencoder.
So now let's compare, again, using MNIST, our input 4s against what we find for counterfactual samples using SharpShooter, gradient descent and latent space, which does not have a specified endpoint along the search path, and gradient descent and input space, doing essentially steepest descent. And this was what I was referring when I was answering Nikita's question about steepest descent and input space. The counterfactual examples have this cloudiness to them because they're making small, almost adversarial changes in input space to essentially trick the classifier. And these would not be valid in-sample data points. What other things to kind of highlight? I think there's some stark differences in our use of the latent space through the projection and just doing gradient descent in the latent space itself. Particularly on some of the odder looking 4s, there is no angular stroke that's possible and be classified as a 9. And yet just steepest descent in the latent space does kind of allow that. This seems to work. Breaking this bit of the crossstroke seems to be effective in fooling a classifier, whereas SharpShooter has kind of kept that single stroke aspect of it, but morphed it into the loop of the 9. And like the 4 above, it just is missing the downstroke. So it's really got, I think it's got a powerful representation in terms of being able to change the bad attributes into good attributes to help get an advantageous classifier. Anything you want to add on this, Matt?
No, I think you did a good job.
Yeah, and like even some of the, it's odd in the just doing gradient descent in the latent space that it can just try to drop some features that like you're removing strokes from the digit that don't seem to be entirely representative. So this is a qualitative kind of, it gives us a warm fuzzy. We look at how this is performing. It's like, yeah, it's doing what we expect. If we look at the quality metrics that Matt outlined in terms of validity, being successful in crossing the decision boundary, being relatively close to the input sample, not changing too many features, not being not having a undetected sensitivity in the classifier, having good reconstruction error, and is timely in being able to predict these. You know, SharpShooter is not always at the top of the list. It does pretty well in 4 out of 6 metrics, and is competitive in the other ones. So I think that's reassuring as well.
Yeah, and so the second data set is pretty interesting. UCI credit default. This was Singapore, and they basically like had this. They were giving out a lot of credit cards, and they tracked who defaulted in this data set. The data set is challenging for a number of reasons. First of all, the classification score here is only about 0.7 AUC. So it's quite bad relative to MNIST. That's getting up there, I don't know, 0.95 plus. And it's also a very high dimensionality, both in terms of these sort of very correlated continuous variables, but also their number of categorical variables to talk about in a second. But it makes it quite a challenging data set. It's a lot of fuzziness here. And I think SharpShooter performs a little worse because of it, but it's still interesting to see sort of what fell out of this. So what we're looking at here are the categorical variables. They're marginal distributions in the 3 methods outlined. So green is the SharpShooter here. You can see that in the first one, it makes SharpShooter makes. So by the way, 0 is centered around the no difference between the base and the counterfactual. So the 2 other methods don't have large changes, and what changes they do have are very normally distributed. Where SharpShooter seems to kind of disregard that and do its own thing, where so this is the first one for the limit balance. You can see we've shifted to the right, so maybe a large limit, a large spending limit on your credit card might bias you against defaulting. And then you can see these bill amounts. So the way this data set worked was like they sort of measured them each month for a number of months prior to like when they've realized the default or not default. And you can see that in general, SharpShooter is shifting all of the later bill amounts downward. So maybe the presumption is that if you had less bills, you are less likely to default. I mean, that doesn't sound too unreasonable. When we look at how much you are paying each month, something kind of curious happens. SharpShooter and again, it's interesting because like the other two are just kind of sit in the middle, but SharpShooter has shifted to the right here for the first one, meaning that we actually expect people to be paying more in the last payment, and then in the previous ones paying less. So it's kind of curious that it both, you know, it wants you to be paying less and borrowing less in all of the earlier bill periods, but in the last period paying a bunch of money. So maybe, who knows what the actual story is here, but maybe the tax collector is knocking on your door and that's when you pay.
Yeah, I think. Well, no, I think there's an element of turning a time series event into discrete tabular data that's dependent on the month. Like each of these bill amount 1, 2 through 6 is a snapshot at each of the months, and the default is at the end of that 6 months. So there's an aspect of, I believe that it's picking up that if you had low bill amount and you paid a lot in the first month, then you would not have defaulted. And afterwards, it doesn't really matter because you've already kind of set yourself up by not having a lot on your bill, you know, regardless of what you pay in the downstream months 2, 3 through 6.
Yeah, that makes a lot of sense. I think I mixed up my which way the amounts went.
That's fine. It's small font size. We'll increase it for the next talk.
And then for the categorical variables, again, there isn't much change in the other two variables, which is kind of interesting. Categorical variables are particularly difficult for gradient methods. It turns out you need quite a large gradient to jump the gap, basically, to force a change in space, and specifically in input space, for it to make that change in a classifier. But here you can see that SharpShooter it prefers being married, and for all of the other periods, it makes you more on time. Go figure. And it does change that you to high school. It seems to prefer high school over the other methods. Like it only requires that you have high school, but maybe that means that this is like a less relevant variable. Interestingly enough, we don't necessarily do much better in UCI. Again, this was a very difficult problem. And for gradient descent in input space, which shows the highest validity, it sort of calls into question because of that difficulty of changing the categorical. So how realistic these are might be another question. For SharpShooter, we do better in the classifier shift. And again, in time, I did notice that time is actually another order of magnitude faster here than in even our other cases because of that extra difficulty of the gradient steps. And yeah, so this is definitely our weakest point, but I think it's interesting that it exposes some points that we'll focus on later in how we're going to improve SharpShooter down the line.
Here's some results on the Lending Club data set. Again, it's whether you're going to default on a loan. And Lending Club is a peer-to-peer lending, or at least used to be at the time of this data set. It would try to rate loans and have people at large sponsor those loans and get the reward of the interest rate when people repaid their loans. This is a relatively low dimensional data set compared to UCI. Just a handful of continuous variables, debt to income, loan amount, interest rate, annual income. The probably most salient is FICO score, your credit score, and the term of the loan. And, by and large, the gradient descent and input space is making the most significant changes. Sometimes, yeah, larger changes than you might anticipate after thinking about the steepest descent aspect of it. In this low dimensional space, I think the latent space for this is just 2-dimensional. There is vanishingly little difference between just doing gradient descent in latent space and SharpShooter. So in some sense, this is almost like a unit test that SharpShooter is in low dimensional space. SharpShooter degrades to just gradient descent in the latent space. And here, as far as quality metrics go, SharpShooter is doing relatively well. It's not stellar in terms of like proximity or any of those metrics, but it is not doing anything outlandish in terms of finding bad quality counterfactuals.
So the last thing that that we sort of discovered through the use of this is kind of a nice way of visualizing what's going on behind the scenes, and that correspondingly told us more about what the autoencoders were doing and what the classifier decision boundary would look like as well. So what we're looking at here are blue points are the target points, green points are the translated bases or the base projections, and the orange points are the bases. And so these points are in the unified autoencoder space, and what you can see, at least for MNIST and Lending Club, is there's a very clean separation between most of the bases and the targets, the blues and the oranges. And this wasn't something that we told it to do. This is something it completely did on its own, which is frankly amazing in my opinion, because there's no labels here, right? This is unsupervised learning. And it somehow managed to separate nearly all of the classes from each other. And then when we've taken the bases and we've translated them through the target autoencoder, it's placed them throughout that space, which is exactly what we wanted. We wanted it to put the bases into their space. And the one that's different here, so these are PCA plots, MNIST and Lending Club. UCI is TSNE. Don't worry if you don't know what that means. It's just a low dimensional visualization technique. PCA does preserve orientation relative to each other in terms of their the dimensions that we see, where the TSNE kind of jumbles things up a little bit. But UCI again was sort of the difficult child, and it does sort of do something a little different. But you can see there's sort of these defined clusters that sort of start to separate out because of the tabular dimensionality. And so this picture is sort of the illustration of the SharpShooter process. So now we've drawn purple lines between the base points and their projections. So one orange is connected to one green. And the really interesting thing about this is that a lot of these lines are somewhat parallel to each other. And if you're familiar with autoencoders and representation learning, there's this like canonical picture of a face, and you give them the face glasses, where they sort of subtracted off this vector, and they discovered that there is a vector for glasses, and so they just added the glasses vector to the person's representation, and then the new one became person with glasses. So you can kind of see that there's a chance that something similar is going on here, where there's like a direction that a directionality to these, which is somewhat reassuring from the validation. And yeah, and then we managed to use these in the next slide where we've taken along these purple lines and we've just taken a whole bunch of points in these purple lines. And now we've classified their score at each of these points, and we've plotted them into these, we've like aggregated them into hex bins, and then we've plotted them here. And this is sort of like this is our visualization of the decision boundary. What we're looking at here is the two colors of the two classes, the classification score specifically. And the black points are the SharpShooter counterfactuals that SharpShooter has found. If we look first at the Lending Club data set on the right-hand side, the classes are very separated. Decision boundary is tight. SharpShooter is putting all of those points along the line with a few notable exceptions. And yeah, I mean, like this seems like, you know, case closed. It's doing very much intuitively what we expect, and the classifier is creating this separation of the two classes, but in a way that corresponds again with the VAE, which is the fascinating part, that the VAE and the classifier have these two different objectives, and yet somehow they're still having corresponding a lot in terms of their internal structure. MNIST, on the other hand, it looks fuzzier, looks like a fuzzy blob, but this is likely due to the fact that Lending Club is, we're looking at 2 dimensions in Lending Club. MNIST, we're looking closer to 20 in the latent dimension. So the latent codes are about 20 dimensional. So if anything, these lines that looked very 2-dimensional in the last picture are just the 2-dimensional representation from the PCA. And so really we have all these lines that are kind of coming in at different angles through this, you know, hyper cloud, and then projected onto a flat 2-dimensional image. And so it's not surprising that that boundary looks less crisp, because there's a lot more actual distance variability in how these plots. But presumably it's doing something very similar to what Lending Club is doing, just in a higher dimension, where it's, again, separating into 2 sort of blobs, hyperspheres. And then SharpShooter is sort of placing again in between those 2 hyperspheres.
Yeah, I think MNIST is such an outlier in a data set since it gets to 99% accuracy. The 4s and the 9s are disjoint. And this fuzziness is really just SharpShooter filling in that space where nothing is in the data set. But yeah, I think that's wicked cool. So we've run through the experiments, the visualizations. Let's just touch on what we think are some of the advantages. I think speed is an enabler. It gives you the ability to both, you know, query a lot of different data points and get counterfactuals on a per sample basis, but it also enables you to calculate a ton of counterfactuals over your large test set and see those distributional shifts that are occurring, you know, as like what is really going on in changing the distribution of each of your inputs, which you don't get on a per sample basis, and you don't necessarily get unless you can crunch a lot of counterfactual explanations. And I think, you know, as Matt alluded to earlier, you know, we're using a beta VAE now. There's a ton of work going on in representation learning as we continue to improve the latent representation. SharpShooter will continue to improve as well. And I think one of the stronger advantages is that it calculates more plausible and potentially even actionable counterfactuals for individuals or for digits, what have you. Disadvantages, however, there's definitely one around training variational autoencoder, or this could also be put in an advantage column, because, you know, if it were straightforward, I would not have had the collaboration with Matt, and we would not have had the opportunity to work on this together. This is not just an off-the-shelf push button kind of thing that you can do. It takes thought and consideration and multi-objective optimization in terms of tuning it. We are going to kick the tires with more data sets, but at what level of imbalance in your labels does this become intractable? You have to have enough of each labeled class such that the inputs from those classes can influence the autoencoders that you're training. Otherwise, it would, if you had 1/10 of 1% of one class, the unified autoencoder would not even pay attention to that very minority class. And Matt, did you have something specific in mind around fuzzy boundaries? Is this the noisy decision boundary of UCI?
Yeah, definitely.
Yeah.
Yeah, it just makes it harder. I don't know if that's specific to our method or if that's actually, that might be more specific to counterfactuals in general.
Yeah, I think that speaks to, quality of the data. UCI it's a snapshot in time. Some of those folks that were labeled as not defaulting, you should consider those labels as have not yet defaulted, because it's maybe still had time to occur later on. And then do you want to take this last one, representation spaces?
Yeah, sure. So one of the other things is again, this could also be considered an advantage, but like at current, some work has to be put into creating a to training the VAE in such a way that the latent space is well fit to the use case. For example, for MNIST, it's a little bit of a simpler problem, but when you get to UCI and higher tabular dimensionality, there are probably more expressive latent spaces that we could use. And so as the research improves on those things, that we can only expect this to get better. But it does remain a little tricky to work with at the moment.
So just to wrap up briefly, we talked about the SharpShooter algorithm, showed some experiments, discussed some advantages, disadvantages, discussed the VAE in its formulation for the target class and its projection capabilities. Matt talked about the novel visualization of the decision boundary and latent space. While our method's not always the most sparse or closest, it's orders of magnitude faster on the data sets, and it really seems to excel at realistic, almost actionable counterfactuals. And there's a ton of future research that we can do on this. Obviously, improving latent space structure, as Matt highlighted, comparison to other counterfactual methods to see how we stack up against them, and obviously add more data sets for more experimentation, and especially check the limits of class imbalance. With that, I'd like to thank you all for your attention and open it up for questions at this point.
Many thanks. Anyone have any questions out there? We are at just about time, but certainly wanted to open that up.
So John, maybe you can ask a few pointed career questions.
Sure. I mean, Nikita and Brian might be able to answer a couple of these. Just basically, can you tell us a little bit about some of the data you're working with daily, not just with examples like what you've been doing with Matt, but things that you do daily that might be of interest to some of the students on the phone. Maybe it's going to be different between what you and Brian are both doing, Nikita, but why not open it up a little bit to the data scientists?
I've got to say, I've got a great job. I work in that boundary between research and trying to find useful things to advance state of the art inside Capital One. So, I work with everything from open source tabular data sets like I showed in this talk to significantly larger data sets of thousands of variables and millions of data points that are typically data that we collect for credit decisioning, that sort of stuff.
Yeah, so since I work together with Brian, so I deal with the same type of data.
Gotcha. Fair enough. Are there, because we've got many students who might be out there looking for jobs or opportunities, can you talk a little bit about what might be a skill you might recommend that all students make sure they have before leaving a program like ours, or data analytics or business analytics or stats when they graduate with a graduate degree here in the master's program? What skill you think is going to be most necessary right now, immediately, and maybe predicting out just a little bit the wish list of what they should have?
So I would go with a strong machine learning background. Knowledge of statistics is never going to be out of date, right? I mean, being able to just straight up analyze data without relying on supervised learning is obviously a great skill to have. I mean, I got a PhD doing computational fluid dynamics. I am not from the start a data scientist. So all of anything that you learn, if you enjoy doing machine learning, can easily be repurposed. I think I'm walking, talking example of that.
Yeah, fair enough. Appreciate that.
Maybe I can add also, if there is any experience that people can get in dealing with large data, with big data, that's helpful in practical setting. Meaning data that is far beyond a single laptop of implementation.
Hi, I'm Ari. I also happen to be someone that works with Nikita and Brian. I recommend. Thanks. I recommend Spark because Nikita mentioned big data technologies. Spark more than anything else in terms of working with big data, but other big data technologies could be really useful as well.
Appreciate that insight. Yeah, it's amazing what recruiters are asking for on resumes, or trying to ensure that they have the right skill sets to match up with jobs and opportunities. But job searching in this market, anybody have any comments about that right now? And there's the cat. There you are, fuzzy cat. Any words of advice regarding maybe job searching, whether it's job or internship right now? How are you seeing the market at Capital One?
The market everywhere is hot. That's all I could say.
Right.
And first of all, we are hiring. Second of all, we love having interns. If you want to kind of try before you buy,
They recommend it.
No, absolutely. And we've had Capital One's been a great partner of ours for a number of years, and certainly does hire DS grads and other students, obviously from Columbia too. So, but we're seeing the same thing. We're getting a lot of recruitment calls, and again, biggest challenge for a lot of students typically might be communication skills. So that seems to be one of the bigger areas that we're trying to work on with a number of things that we do here internally. So, but very good advice. Alexis, anything else?
I think we're good. We went a little over, so
Want to be mindful of time for sure.
Okay. Well,
Thanks again.
You so much.
Thank you, everyone.
Thanks, Matt, Nikita, for joining us. Ariel, especially, and Brian, thank you for your time. Enjoy Schenectady. Best of luck with the snow. It's coming, right? It's coming.
It's coming.
Yeah,
coming.
fair
Thank
enough.
you.
All right. Thank you very much. Alexis, thank you. Have a great night.
Yeah, thank you all.
Okay, good night.
Bye all.
Bye-bye.